this tutorial, we are going to be talking about solubility curves. Solubility curves are really easy to understand, and they are literally just a picture that shows you how solids and gases dissolve in water at specific temperatures. So there are lots of different types of solubility curves out there, meaning they don't all look like this one, but they all tell us the same thing. Someone somewhere has done this work. They have taken as many substances as you can imagine, and they have dissolved these substances in water at specific temperatures, and they've taken that data and they've made a graph. And this is really handy if you're working with a certain substance in a lab or an industrial setting. You can always look at the solubility chart to see how much stuff you can dissolve at a certain temperature, and that could be really handy. So we're going to start with just a general definition of a solubility curve. A solubility curve is a graph that shows the solubility of solids and gases over a specific temperature range. Now, some important things you need to know about a solubility curve. The y-axis represents the grams of solute dissolved per 100 milliliters of water. The x-axis represents the temperature. Also, you need to keep in mind that a milliliter and a cubic centimeter are the same thing because that may show up. Now, a solubility graph is based on 100 milliliters of water. You've got to have some standard measurement of water, because if your amount of water was never the same, then your data would be wrong. So it's always based on 100 milliliters of water. Often you will see that written as 100 grams of water, and that's because the density of water is really close to 1.0. So just keep in mind that amount of water is very important, because if you double the amount of water, you're going to double the amount of solute that your solution can hold. For example, if you were to half the amount of water, then you would half the amount of solute that your solution could hold. So here's just a small little version of a solubility graph, and you can see on this one, and this is going to be like the one we look at today, we have our grams of solute per 100 grams of water, and we have our temperature, and it is in degrees Celsius. Now, this particular solubility graph shows us solids. We know that because you can see that as temperature increases, the solubility is increasing. And we also see a couple gases on this graph. As temperature increases, the solubility is going down. This is very typical of a solubility graph. There'll just be more than one substance on it, so you're not toting around 15 graphs to show a student. This is just kind of a one-stop shop. If there's a particular substance you work with a lot and it's just that substance, you just may have one curve on a graph. So this is just saving space. Now, we're going to look at a generic solubility curve for a solid. And what you need to know about a solid is that when temperature goes up, the solubility goes up. Also, it's important to point out that pressure does not have an effect on the solubility of a solid, and what that means is you can't increase pressure to make it more soluble. It's not going to happen. So for a solid, we're going to have our grams of solute, and we're going to have our temperature. And for a solid, a general solubility curve is always going to move in this direction, because as temperature goes up, let's say it was going 10, 20, 30, 40, 50, 60, 70, 80, your grams of solute that you can dissolve are also going up. So at this temperature, for example, whatever it happens to be is a lower temperature, you're going to dissolve this many grams right where they intersect that line. At this temperature, a little warmer, you're going to dissolve more grams of solute. So a solubility graph is really easy to read. And what's happened is someone took this substance, and at every temperature, they just experimentally figured out how many grams of solute could be dissolved. So all the points on this line represent what we call a perfectly saturated solution. Now, a good example of this would be table salt. You could also think of sugar. If you have a sore throat, for example, and you're going to make a salt solution to gargle, we know that if the water is warmer, you're going to dissolve a little more salt. Everybody in the South knows when you make that good sweet tea, when do you add those 2 cups of sugar to that gallon of tea? When it's hot. Pour that sugar in, shake it up, stir it up. You might have noticed that when the tea cools off, sometimes some of that sugar will settle out of the solution, and that's because as a solution cools, it can't hold as much solute anymore, and what it can't hold will always fall to the bottom. So those are just 2 good everyday examples to help you remember this concept. When temperature goes up, the solubility of a solid goes up. And again, remember, pressure does not have an effect on the temperature, on the solubility of a solid. Now, let's take a look at the solubility of a gas. And this is a little bit different. And I always like to point out, students will usually ask me, what do you mean dissolving a gas in a liquid? How do you do that? You've seen it lots of times in your life. You probably just haven't thought about it. So when we dissolve a gas in a liquid, when temperature goes up, the solubility actually goes down. Gases do not like to be dissolved in warm liquids. They like to be dissolved in cold liquids. Also, I want to point out that pressure actually has an effect on the solubility of a gas. For a gas, when pressure goes up, the solubility actually goes up. And I'll go ahead and give you an example of this. Think about your canned soft drinks. When your soft drinks are canned, they use pressure to push that CO2 down into the soft drink. I'm going to assume it's probably cool because it's going to, your soft drink's going to hold more of those nice bubbles that we like when it's cool. So I'll move down here and go and give you the example. Carbonated drinks are a wonderful example of dissolving a gas in a liquid. Also, the dissolved oxygen in lakes. Any of you who may be avid fishermen may know about this. Certain fish have certain dissolved oxygen requirements, so you may find certain fish at certain depths. Fish that need more dissolved oxygen may be deeper in the lake where it's cooler or in an area where it's cooler. Sometimes we'll see on the news that maybe there's been a bunch of fish found dead in a lake, and scientists or biologists are trying to figure out what happened. Sometimes it's because there's not enough dissolved oxygen and the fish literally have suffocated. So if you have a fish tank, you probably have some way to add oxygen to the water so that you can ensure your fish are getting plenty of oxygen. So those are just some things to think about. Now, the solubility graph for a gas looks something like this. We still have our grams of solute and temperature, but what we see is the curve goes in the opposite direction, because as it gets hotter, we're going to dissolve less. At cooler temperatures, we're going to dissolve more. And again, all of these points on the line make up a saturated solution. Now, let's take a look at just a little bit more information, and then we're actually going to practice reading the chart. The first thing, before we get to that I want to go over with you are the different areas on this chart. So I'm going to use a solubility curve for a solid just as an example. The same thing would work for a gas. And again, we're going to put our grams of solute and our temperature. Now, you've already heard me say that all of the points that make up this line represent a saturated solution. That's just my abbreviation for saturated solution. A saturated solution is a solution that contains the maximum amount of solute at a given temperature. At this temperature, we can hold exactly this much, and so on and so forth. Now, sometimes we don't dissolve as much as we could have, and we call that an unsaturated solution, and that represents all the area under the curve. So let's say for whatever the substance is, at this temperature, maybe we dissolve this much. Well, we could have actually added more to bring us up to this line. So all the points under the curve represent an unsaturated solution, and an unsaturated solution basically contains less than the maximum amount of solute at a given temperature. And I'll have these definitions up for you in a second so you can copy them and have them for your notes. And sometimes we try to put too much solute in our solution, and that's called a super saturated solution. That's where we've actually added more solute than that solution can hold at that temperature. Now you might say, well, how does it hold it then? It's really not. In order to keep your solute, I'm going to say kind of air quotes, in solution, you're going to have to be agitating it the whole time. You're going to have to be stirring it or shaking it, because as soon as you set it down, anything above that curve that you've added is going to fall out of solution. But it kind of go back to the sweet tea example. If you add a lot of sugar to tea when it's hot, it may dissolve all of it, but if that tea cools down, your temperatures come down, so your amount of solute you can hold has also come down, and you're going to come back down to that line. So a supersaturated solution contains more than the maximum amount of solute at a given temperature. So here are your definitions, and you might want to pause the video here and just make sure you have these written down so that you know all the different parts of a solubility graph. Now at this point, we are ready to read the graph, and I think you're going to be pleasantly surprised at how easy it is. It's, again, just a really useful, handy piece of reference material to have when you're working with a substance in a lab, or you just need some general information. So let's take a look at the first question, and I'm going to have some graphs handy so that I can show you how to read them. So our first example says, what mass of sodium nitrate is required to make a saturated solution in 100 grams of water at 40 degrees Celsius? Well, first of all, this is just telling you or reminding you that that whole graph is based on 100 grams, 100 milliliters of water. You don't have to do anything. It's just important to note, okay, they're looking at exactly what the graph is based on. So we're looking at sodium nitrate, which is right here. So this is the line that we are focused on. And the question says, at 40 degrees, how much can we dissolve to make a saturated solution? So what we're going to do is we're going to go down here, and I'm going to have to move this around a little for you. We're going to look at 40 degrees, which is right here. So you are going to follow 40 degrees up to, you can see I went all the way up to that sodium nitrate line, and then you're going to come over here to your grams of solute. And this looks like about 105 grams. So at 40 degrees Celsius, we can dissolve 105 grams of sodium nitrate in 100 grams of water. So our answer is 105 grams. Let's look at the next one. What mass of potassium chlorate is required to make a saturated solution in 100 grams of water at 80 degrees Celsius? Again, they're just reminding me, hey, I'm talking about 100 grams. That's what the chart is based on. We're looking at potassium chlorate, KClO3. So this time we're looking at this curve right here. Get that where you can see it. And we're asking about, I believe, 80 degrees Celsius. So you find 80 degrees Celsius, follow it up to your line, bring it over here to your grams of solute, and it looks like about 40 grams. Now you hear me saying about because we're going by tens here. It could be a little subjective. Someone might say, oh, it looks like 41 or 39, but we're going to say about 40 grams. And that's your answer. So let's look at another one just like this. What mass of potassium iodide is required to make a saturated solution in 100 grams of water at 20 degrees Celsius? Again, a reminder, hey, that chart's based on 100 grams of water. And this time we are looking at potassium iodide. Now, potassium iodide is super soluble. When you look at your chart, like, it is way up here. I always think that's pretty interesting because at 0 degrees Celsius, you can dissolve 130 grams of potassium iodide in 100 grams of water. That is just crazy soluble. So we're looking at 20 degrees Celsius. So 20 is right here. We are going to take that 20 all the way up to the potassium iodide line. We're going to follow it over. I'm going to say we're looking at about 147 grams. Now, while we're talking about that, I do want to point out, when you look at a solubility graph, it also tells you a lot about how soluble it is. For example, potassium iodide looks like it's just going to dissolve very quickly. Sodium chloride, the line's kind of hard to see. I know there's a lot of lines on here, but sodium chloride right here, look from 0 to 100. Its solubility really doesn't change very much. At 0 degrees Celsius, you're about at 37 grams, and at 100, you're just barely reaching 40. So temperature does not affect the solubility of sodium chloride, maybe as much as it affects the solubility of something like potassium nitrate with this very steep curve. So different substances are affected differently by temperature. But if it's a solid, the general direction is always going to be moving in that upward direction because solubility does increase, but for different substances, it is different. Just wanted to point that out. Now, let's look at this one because this one's got something a little different in it. What mass of potassium iodide is required to make a saturated solution in 200 grams of water at 20 degrees Celsius? Now, that 200 is important because the graph is based on 100 grams. So once we find, so we're going to read the graph for 100, which we've already done, and we knew that at 20 degrees Celsius, we could dissolve about 147 grams in 100 grams of water. So if we're talking about 200 grams of water, we're going to have to double that amount. So 147 times 2 is actually going to be closer to 294 grams. So again, that's where you've really got to pay attention to what they're giving you here. Normally, this didn't affect anything you did in the other problems, but because we suddenly see, oh, 200 grams of water, I've doubled the amount of water, I have to double the amount of solute. So you read the chart as is and then just double it. Now, there's a couple other types of questions that you might see on solubility. Just, you know, you're still reading the graph the same way, but maybe they're worded just a little bit differently. So we're going to look at some of those. At what temperature will 50 grams of potassium chloride form a saturated solution in 100 grams of water? So the reason this one is different is because they're giving me the grams of solute this time. So I'm looking at potassium chloride, which is right here. And they are telling me in the problem, I'm interested in 50 grams. Like, what temperature do I need to be at to make that happen? So you find 50 grams, and this time you just follow it over to the right to potassium chloride, and where you intersect that curve, you drop it down, and that's going to happen at 80 degrees. So if you really wanted to dissolve 50 grams of potassium chloride in 100 grams of water, and you wanted a perfectly saturated solution, that's going to happen at 80 degrees. If 20 grams of ammonium chloride is dissolved in 100 grams of water at 60 degrees Celsius, what type of solution will result? So this time we're looking at ammonium chloride, which is right here. Okay. And they're telling me, all right, we dissolved 20 grams at 60 degrees Celsius. So they gave me those coordinates. So 60 degrees Celsius, 20 grams is right there. So we're looking in reference to ammonium chloride. They're telling me in the problem at 60 degrees, we dissolve 20 grams. Now what you can see is this is well below that curve. So we have an unsaturated solution. Now we could go even further to say, since this is going by tens, we could add 10, 20, 30. We could add about 35 more grams before we reach that saturation point. So this would be an unsaturated solution because it's below the curve. The points that the intersecting points they gave me were below the curve. That's how we know that. And if we did that and wanted to add enough to make a saturated solution, we just found that it would be about 35 more grams to reach that point. And again, I'll show you that. We were here, 10, 20, 30, about 35 grams. So that's how you read a solubility graph or solubility curves. All the examples I did today were actually solids. I'm not sure why I didn't do any gases. You read gases exactly the same way, but just keep in mind the basics. For solids, when temperature goes up, solubility goes up. Therefore, you're going to see your curve move in this direction. For gases, when temperature goes up, solubility goes down. You're going to see the curve move in that downward direction. And just remember, this graph is not complicated. It is simply a picture showing you at very specific temperatures exactly how much stuff can be dissolved in 100 grams of water.